The execution of a quantum algorithm requires us to prepare states, perform quantum circuits on them, and then to read out the result. Today, we're going to introduce a commonly used technique for this final step, which uses some relative phases. These phases, which are numbers of the form e to the I phi, play a very important role in quantum mechanics, quantum information, and quantum computation. Every unitary operator can be written out in its eigenbasis, and its action is reduced to a set of these phases. If we put one of the eigenstates in, the output is the same state multiplied by that phase. If a phase is randomly applied to some of the components of a quantum state, this decoheres the quantum state. So keeping track of phases is important even at the physical level before we discuss any quantum algorithm. Nevertheless, many quantum algorithms do involve the accumulation of non-random phases, so it's convenient that there's a way to read these phases out, which we'll derive in this lecture. Let's first look at the simplest of all phases, the global phase. If we had an operation that multiplied a state by a global phase, like a unitary does when one of its eigenstates is input, the output probabilities that are defined by Born's rule don't change. This means that the global phase has no physically measurable effect. Nevertheless, we can define an operator V alpha which multiplies any input state by a global phase. It's pretty simple, just e to the I alpha times the identity. Nothing special. However, something interesting does happen when we define a controlled V alpha operation. A phase is accumulated on the one component of the state of the control qubit. This is a stark contrast to the normal way of thinking about controlled operations, in which something happens to the target qubit depending on the state of the control. This implies something called phase kickback. If we apply a controlled U operation to a register where the target subsystem is prepared in an eigenstate of U, then U acts like the V alpha operator, and the corresponding phase is transferred to the control qubit, where it can then be read out in principle. Even in the case where a single readout doesn't specify the phase exactly, this procedure can be repeated since it doesn't alter the input state psi k. This is still the case if the target register contains many qubits or other types of quantum systems. The versatility and simplicity of using a single qubit to read out the action of an arbitrarily large unitary is what makes phase kickback an important building block for quantum algorithms.